Module 1, Part 2 will discuss the OSI reference model. I'm sure you've heard of the OSI reference model, and you've probably even studied it before. This module will take a look at the way Cisco views the OSI reference model. The OSI reference model was created by something called the International Organization for Standardization. ISO actually is the Greek term for equal. Why should we use the OSI reference model? The OSI allows us to divide the network communication processes into smaller and simpler components, which aids component development, design, and troubleshooting. Changes in the OSI model at one layer do not affect other layers. And it encourages industry standardization by defining what functions occur at each layer of the model. Now remember, the OSI reference model was designed for application developers and manufacturers of hardware equipment. It's not for use for us on a day-to-day basis. So we wouldn't wake up one day and say, I think I'll use part of the network layer today and part of the presentation layer tomorrow. It doesn't work that way. We will use an application that has used the specifications from the OSI reference model to help us have interoperability between disparate systems. Let's take a look at how the OSI reference model is grouped into functions and layers. First off, we have 7 layers. Layer 1 being the physical layer, and then going on up through layer 7 in the application layer. The application layer is responsible for file, print, message, database, and application services. Basically, the application layer is responsible for network services. The presentation layer will give us translation services. And the session layer will help us have dialogue control, which means it's going to keep application data separate from other users' applications data. Now, the top 3 layers are typically called the upper layers and are grouped into a section as shown in the slide. I grouped them into 3 different layers: the bottom layers, the middle layers, and the upper layers. And again, the upper layers are used by application developers to communicate to the user interface. We would use the middle layers and the lower layers. The middle layers help us take a data stream from the upper layers and reliably rebuild that data stream on a remote host. Or it even could be a local host on our LAN, but nonetheless, it's another host. The bottom layers allow us to take this data stream into smaller segments, place them into packets, and put them onto frames on our LAN to either communicate to a host on our LAN or to our router, because the packet inside the frame is destined for a remote network or a remote host on a remote network. We're going to talk about segments, packet frames, and bits in the upcoming section. Let's take a look at the application layer examples that I have on the screen. First, Telnet stands for telephone network. That's because that's how most communication used to occur. And basically allows my terminal to be a dumb terminal and communicate and run applications or programs on another host. FTP and TFTP are file transfer protocols. TFTP stands for Trivial File Transfer Protocol and is the baby brother of FTP. Simple Mail Transfer Protocol allows us to send mail. Hypertext Transfer Protocol is used to view web pages on a website on the internet. Now we have HTTPS. It really stands for Secure HTTP. It allows us to have secure communication, viewing websites, and so on. Simple Network Management Protocol, or SNMP, allows us to manage and monitor our network. DNS, or Domain Name Service, allows us to resolve host names to IP addresses so we can communicate on the internet or even on our local network. Now, I want to talk about some terms called connection-oriented service and connectionless network service. And basically, a connection-oriented service means we're going to receive acknowledgments and we're going to have a reliable session. Now, notice I didn't say guaranteed session. So there's no such thing as guaranteed delivery, even in the real mail service that we have in the world today. Even though they may say they're guaranteed, they're more reliable than just regular postage. For example, if we go to a post office and we take a letter and we put a stamp on it and put it in a mailbox, does it get to its destination? The answer is probably. It probably does. I always get my bills. But the reality is that if I really wanted to make sure something got to a remote host, data got to a remote host, or my landlord received the check in the mail, I really want to verify that this landlord received this, and I want to get a receipt, I would use a connectionless service or maybe like a registered or certified letter, right? So a connection-oriented session is more like a certified or registered letter where I will get a receipt saying that they did receive that letter or that check. However, it's going to cause overhead. In other words, I have to go to the post office and I have to park, stand in line, fill out extra paperwork, and pay extra postage to be able to get this connection-oriented service done. Data is the same way. If I use a telnet session, for example, what that means is I'm going to use a connection-oriented session, and I'm going to set up my virtual circuit before I send my data. This is called overhead. Let's take a look at the screen again and talk about the different applications that are connection-oriented versus the applications or programs that are connectionless. First, telnet is connection-oriented, which means, if we say that, it means it uses what's called TCP, or Transmission Control Protocol, at the transport layer. FTP is also connection-oriented, which means it uses TCP at the transport layer. Now, if I don't want to have a connection-oriented program, I'm an application developer, I'm not an end user, and I say I want to create an application that's not connection-oriented. Which protocol can I use at the transport layer? Well, you have a 50-50 chance because there's only two. TCP, which stands for Transmission Control Protocol, and UDP, which is User Datagram Protocol, and UDP is connectionless, TCP is connection-oriented. So if I'm an application developer and I say I want connection-oriented services with my program or application, I would use TCP at the transport layer. If I'm an application developer, and notice I keep saying that because I'm trying to get it through to you that you do not choose this. If I'm an application developer and I want connectionless services because I want faster delivery, not reliable delivery, I would use UDP at the transport layer. Both of these protocols will go through IP to deliver their packages or segments of data down to the network layer, which would become a packet when IP gets a hold of it. And again, we'll talk about this more in a minute. But nonetheless, we cannot skip IP. It's kind of like all roads lead to Rome. All protocols go through IP. We just need to remember that. So let's go back and talk about these applications or programs again. Again, as we mentioned, Telnet used TCP, which means it's connection-oriented, and that's how we determine that it's connection-oriented. FTP is connection-oriented. So tell me, is SMTP, Simple Mail Transfer Protocol, is that connection-oriented or connectionless? In other words, I'm asking you, does it use TCP or UDP? And the answer is TCP. It is connection-oriented. TFTP, Trivial File Transfer Protocol. Since it's FTP's little brother, I guess we can assume it uses UDP, which means it's connectionless. HTTP, what does it use, TCP or UDP? Is it connection-oriented or connectionless? And the answer is, it is connection-oriented, so it uses TCP. Or it uses TCP, so it's connection-oriented. I guess you could say that either way. And secure HTTP would be the same, right? We know that would be connection-oriented. SNMP, Simple Network Management Protocol. The answer is connectionless, uses UDP. However, there's a new version, SNMP version 3, that's coming out, or has been out actually, that uses both TCP and UDP. But if you're studying for your Cisco exams, as far as you understand at this point, SNMP is connectionless and uses UDP. The last one is DNS, or Domain Name Service. And what does that use? Is it connection-oriented or connectionless? Does it use TCP or UDP? And the answer is yes, both. The only protocol on this page that uses both TCP and UDP is DNS, or Domain Name Service. The presentation layer is used to ensure that information sent by the application layer of one system will be readable by the application layer of another. This is the only layer that can actually translate or change the data. No other layer is capable or allowed to do so. The session layer is responsible for keeping application data separate. It doesn't really do as much as the other layers, really, but it is responsible for dialog control and making sure that the application data is not readable by another application user. Now, the transport layer is probably the most important layer for us. In other words, this is where we're going to have our reliable services using TCP, creating a virtual circuit, or using UDP and having connectionless service. But this is where we receive a data stream from the upper layers, and we segment that data into smaller pieces and hand them down to the network layer to be routed through the internetwork. So the transport layer is very important and will not be skipped. Again, a host will send a data stream. So remember, our PDU, and I'm going to explain what a PDU is in a second, will be sent down. It's called data in the upper layers. It will be sent to the transport layer. At this point, our PDU will be called segment. Let's talk about the PDU, or protocol data unit, for a second. The PDU by itself means nothing. It is a definition of data as it is encapsulated and is going down the OSI reference model. For example, NetBIOS works in the upper layers of the OSI model, the upper layers being what? Session, presentation, and application layers. Now, the user interface communicates to the upper layers. The user interface is not part of the application layer, as most people would think. For example, a lot of people would think, say, Microsoft Word works at the application layer, and this is not true. Microsoft Word works and communicates to the user interface, which communicates to the application layer. So the NetBIOS would comprise of all the specifications from the upper layers, create a data stream from the user interface, and take that data stream and hand it down to the transport layer. The transport layer would then take this data stream and segment it into smaller pieces. So we call this segmentation. We would then number each segment, and we call this sequencing. This way we can put the data stream back together again at the remote host. Whether it's even a local host on your local LAN or pass a router on another remote LAN, the transport layer would not know that. It would just number each one so the data stream could be put back together in a proper order. There's one more thing that it would do is flow control and acknowledgments. And even though I said that was one thing, it's two separate pieces that work together. And again, if I'm talking about the transport layer and I'm talking about this reliability and virtual circuit pieces, what I'm talking about, we have sequencing, we have flow control, we have acknowledgments. All this is part of the transport layer, and when I talk about TCP, or transmission control protocol. So it's very important that we understand how a reliable circuit is set up, or what we call a virtual circuit, is set up and used at the transport layer. So again, to repeat what I had just said about the transport layer, and there's two protocols there, TCP, transmission control protocol, and UDP, user datagram protocol. TCP being connection oriented, which means that we have segmentation, sequencing, and flow control using windowing. And UDP, which is connectionless, user datagram protocol, we have two options. An application developer only has two options at the transport layer, connection-oriented or connectionless. I guess there could never be a third option. But again, the PDU, or protocol data unit, is called a segment at the transport layer. Now remember, the segmentation does not occur, or the PDU does not have a name until the TCP header or UDP header is put in front of the data that is pulled off from the data stream. So we have a data stream, we take a small piece off, we put a TCP or UDP header on it, it is now called a segment. Before that, it's called data or a data stream. This segment is then handed down to the network layer to be routed through an internetwork. But before we talk about that, let's talk about the transport layer a little bit more. We talked about the reliable session that can happen at the transport layer. Remember, it doesn't have to happen. This is if we're using TCP. And so remember that no session is guaranteed, but it can be reliable if TCP is used. So remember that no connection is guaranteed, but it can be reliable if TCP is used. TCP is a great protocol, and that's why application developers love it, because it works so hard for you, and you don't have to do anything to get it to work. It just does this for you. A reliable session means if you're using TCP and you're setting up a virtual circuit, that means we're going to use port numbers. Now, we're going to talk about port numbers more in the next couple slides, but basically these are numbers that help identify our source port and our destination port at the transport layer. At the network layer, what would we use to identify our source host and our destination host? That answer is IP addresses. At the data link layer, what addressing will we use? Well, there is no remote host past a router in this case. We're talking about only local hosts on our local LANs, and we would use MAC addresses or hardware addresses. So let's talk about a reliable session again, or a virtual circuit. To have a virtual circuit, this means we're going to sequence each segment. So we're going to pull segments of data off from the data stream and sequence them, number them, so we can put that data stream back together again. We will have a flow control mechanism to help control the speed from the receiver to the transmitting device. So what this means is the receiver can control the transmission speed from the source host, so the receiving host does not overflow its buffers. And lastly, a virtual circuit or reliable session means that acknowledgments will be used. And TCP by default uses something called windowing, and we'll talk about that more in a minute. Now, to create the virtual circuit, we have to have a source host and a destination host. We have to first resolve the names, because if I did say Telnet Sally, I would have to know what her IP address is. Then I'd have to determine if she's on a local host, in other words, she's a local host to my network, or if she's a remote host, means pass a router. Because if she's past the router, where do I actually send the packet? I send it to the router, and the router will forward that. That's why we'll call it a forwarder at times. The router will route that out an exit port. Now, to set up a virtual circuit, let's take a look. We're going to use what's called a three-way handshake because we use 3 packets to do this. We're going to synchronize, we're going to negotiate the connection, and then we're going to acknowledge this. Now, what this synchronization and acknowledgement means is that we're going to set up our sequence numbers, acknowledgement numbers, and window numbers. How much data can be sent at one time before an acknowledgement is even received. We'll talk about windowing again in a minute. Now, after this three-way handshake is set up, we'll have a connection established. We cannot send any data, any segments of data, until this connection has been established. Once this virtual circuit is set up, and remember, we're using port numbers. This is how the destination host can have multiple source hosts communicating to it at the same time with a connection-oriented session by using port numbers. The source host actually makes up a port number and says, hey, I feel like being port number 2000. Now, anybody that communicates, let's say the destination host is a server, anybody that communicates to this server cannot use source port 2000 because Bob, let's say Bob is trying to communicate to the server, is now using source port 2000. Now, how many port numbers are actually available on a destination host or destination server, regardless of what it is? 65,535 minus what's known as well-known port numbers, which are 0 to 1023, and we'll talk about those more in a second. So before we talk about port numbers, let's talk about flow control a little bit more. Flow control can occur at the transport layer, but remember, it can occur at other layers depending on your protocols. But if you're using TCP and IP and just running over Ethernet, you're only using flow control at the transport layer if you're using TCP, of course. So some common types of flow control are buffers, which means that the destination host basically has place in memory to take the incoming packets in to digest them or process them. Source quench messaging and stop and go are older forms of flow control. Come back to that. So we use congestion avoidance and random early detection with wireless networks. We don't typically use those with our TCP and IP networks unless it's some proprietary communication. And lastly, windowing is what we use by default if we use TCP. So if an application developer decides to use TCP and IP to communicate between hosts or host to a server, then we're going to have flow control with windowing by default. Now let's take a look at how buffers work on a host. A sending device will send to a receiver many segments of data. Okay. A sending or transmitting device will send data as fast as it can to a receiving host. That's its job. Try to send data as fast as possible, in a reliable fashion, hopefully. Now, if we have plenty of packet buffers, or what we just call buffers, on a receiving host, we're fine. As the packets come in, they're first in, first out, or FIFO, and the receiving host will process the packets on a first-come, first-served basis. However, this only works great if you have plenty of packet buffers. If you run out of memory and you're not using any type of flow control, the receiving device will start dropping packets. So again, flow control allows the receiving device to control the transmit device speed. Now, stop and go or source quench messaging worked, they're similar to this. They worked a little bit different, but this is close enough. Stop and go basically said that the receiving device, when the buffers were full, would send a stop or source quench message back to the transmitting device, and basically it would stop transmitting. And then what happened is the receiving device would process the packets. Once it was done processing the packets, it would then tell the transmitting device to go, start transmitting again. However, the problem with this is the transmit device would say, oh, I get it, you're slower than I am, so I'm going to start transmitting to you at half the speed I was before. So this is not a good solution because we had many problems where just a small problem would occur in the network and the transmitting device would cut its transmit rate in half. This would not work in today's network. Let's take a look at how windowing and acknowledgments works with TCP and see why this is a much better solution today. The sending device will send the agreed upon amount of bytes that are determined when the virtual circuit is set up. So we determine how many bytes of data called a window size can be sent to a receiving device. So when I'm a transmitting device and I say, hey, Mr. Server, I want to transmit to you, the server would then send back and say, okay, I can take 8,190 bytes. A Windows device would do something like that at a time. So the transmit device would send that, then wait and expect an acknowledgement after that. So windowing means that we're going to have a window size and an acknowledgement, and we're going to set up our acknowledgement numbers, what numbers we're going to start with, and what am I going to expect next from the transmitting device. Let's take a look at this slide and see how simple windowing and acknowledgement works if we have a window size of 3. It can't get any simpler than this. The sender in this case has many segments or packets to send, and in this case we send 3 segments, and we receive from the receiving device an acknowledgement of what they're expecting next. So in this case they acknowledge 4 and we say that's great because we sent 1, 2, and 3, so we're going to send 4, 5, and 6. Again, we have a window size of 3. How many bytes can we send and then expect an acknowledgement, and what is the acknowledgement numbers? So we set this up when we set up the virtual circuit. We know the exact acknowledgement numbers that are going to be sent from the transmit and to the receiving device, and the receiving device is going to acknowledge those. In this case, 4, 5, and 6 were sent, but we receive an acknowledge 5, which means we know we received segment 4 because we're acknowledging that by saying what we're expecting next. We don't know if 5 and 6 was received because we're receiving ACK 5. So at this point, we stop, send byte 5, and see what they acknowledge. In this case, if they acknowledge 6, that means they did not receive 6 and are now expecting 6. But in this example, they send an acknowledge 7, so that means they're expecting 7 and already have 6. Then we would send 7, 8, and 9. Let's go ahead and take a look at the network layer. The network layer is the layer at which routing occurs. And the PDU, or protocol data unit here, is called a packet. Now, what was the PDU at the transport layer? That's right, segment. And the PDU at the upper layers, data. So from the upper layers, the PDU is data, segment at the transport layer, packet at the network layer. Now, the network layer has many protocols at work here, the most famous being IP, or Internet Protocol. This provides routing through an internetwork and logical addressing. We took a look at a screen like this earlier, but let's go through this one more time. A host here has a packet that needs to be sent to 172.16.10.5. We could say simply that someone pinged that packet internet groper, which works at the network layer, and we'll talk more about that program later. But we pinged 172.16.10.5. The first thing that happens is that local host must determine if that packet is destined for the local network or remote network. Once it makes that decision by comparing the destination IP address with its own IP address, it'll then decide to send it out as a broadcast on the local LAN or send it directly to the router's interface using the destination MAC address or hardware address of the router's interface. Remember, it must get the hardware address by using the protocol called ARP, or Address Resolution Protocol, which we'll talk about in Module 2. Once the router receives the packet of information, it will look on E0 interface. It will use the information and look up in its map of the internetwork, called the routing table, to decide which interface to send it out of, in this case, serial 0. What we want to make clear on this screen here is that MAC addresses are only used on the local network. In other words, we either send it to our local host by broadcasting it, or we send it to the router, the default gateway. There's not a third option. Once we get to that router, the frame or the hardware addresses, in this example, are discarded, and we just have the original packet that was created on that host. The router then routes it to the remote network. Once it is received on the remote network, in this example, E0 of the second router, the hardware address of the remote host, in this example again, 172.16.10.5, must be found. We cannot send data to the IP address. We must have the destination hardware address. Let's talk about the data link layer. First off, let's talk about PDUs, or Protocol Data Unit. Remember, in the upper layers, it's called data, the transport layer segments, the network layer packets, and at the data link layer, I've mentioned it many times, frames. And below that, at the physical layer, we're going to call them bits. We're going to go over that encapsulation method again in a few minutes. So we're going to frame packets and send them out on the local network. We have two places to send them, as I've already mentioned many times, to a local host being broadcasted on my broadcast domain, or I'm going to be sent out to my router. Those are the only two places I can send a frame. Unlike any of the other layers, we actually have sublayers at the data link layer. Let's take a look at them. The sublayers of the IEEE data link sublayers are logical link control and media access control. Media access controls tells us how we can take packets from the network layer and place them on the local network. For example, we can use Ethernet or we can use wireless. The IEEE committee for Ethernet is called 802.3, which stands for February of 1980 Committee 3. 802.11 is our wireless committee, isn't it? We also have 802.2, which is our LLC, or Logical Link Control Management Committee. I want you to understand that the LLC, or 802.2 committee, does nothing by itself, but it adds functionality to existing IEEE standards. Now, something at the MAC layer that we must understand is something called MAC addresses, or we call them hardware addresses, burned-in addresses, but this is where they get the term MAC address because this is where they're defined. So again, hardware addresses, or MAC addresses, are defined at the MAC sublayer of the IEEE data link layer. Remember, packets use logical addresses, or IP addresses. At the network layer, we use port numbers with our segments. So again, let me go over those. Segment at the transport layer using port numbers. Packets at the network layer using IP addresses. And at the data link layer, we use frames with MAC addresses, or hardware addresses. Now, a MAC address is sometimes called a burned-in address because it's burned into the NIC card, every card purchased and manufactured. So we should have a unique MAC address for every NIC card that we purchase. Now, this is a 6-byte address. Now, a byte is 8 bits, so 6 times 8 is 48. That means we have a 48-bit MAC address, or 6 bytes long. Let's take a look at how we do binary to decimal conversion as well as binary to hexadecimal conversion. If we want to do a conversion from binary to decimal, this is how we would do it. We'd start on the very right-hand bit using a byte, which is 8 bits. So we take 1 byte of data, and we convert that by giving each bit a value. On the right-hand side, the bit values start at 1, and they double as they move to the left. So they go 1, 2, 4, 8, 16, 32, 64, and 128. What we do is the bytes that have any bits turned on, we add those values up. If we look at the first example, they have no bits on. So that byte value is 0. The decimal value is 0. In our second example, we have 4 bits on. The 1 bit on, the 2 bit on, the 4 bit on, the 8 bit on, but the 16, 32, 64, and 128 bits are not turned on. So what we want to do to get our decimal value is add up the bits that are turned on. In this example, 8, 4, 2, and 1. So 8 plus 4 is 12, plus 2 is 14, plus 1 equals 15. We have a decimal value of 15. It's very simple. Now, it's a lot easier because on the screen I had the decimal values actually there. So if we had to do this without the decimal values, or the bit values in this case, then it might be a little bit harder. But you just need a little bit of practice, and this becomes very simple. If you are studying for Cisco certification, this is a critical part here. The third one down, the third example down, we have the 64-bit on, the 16-bit, the 4-bit, and the 1-bit turned on. So 64 plus 16, so let's take a look here. 64 plus 16 is 80, plus 4 is 84, plus 1 equals 85. Let's take a look at our fourth example. Go all the way over here. We have I always start with the highest number. It's easier for me to add. I have the 128-bit on, the 2-bit, that's 130, plus 1 is 131. Our fifth example, we have the 16-bit on, the 4-bit on, that's 20, plus 2 equals 22. And the last bit on, let's take a look here. Goodness, we have every bit turned on. Let's add these up. 128 and 64 is 192, plus 32 is 224, plus 16, 240, 8, 248, plus 4, 252, plus 2, 254, plus 1 equals 255. So we can see a byte value from our first example with no bits on is 0 all the way to 255. Now that's 256 numbers. That would become important in section 4 of IP routing. Now, we need to also take binary numbers and convert them to hexadecimal. Let's take a look on how we can do that. So taking a look at our binary to decimal examples, what is the hex equivalent of each of these binary numbers? Now, these are the same numbers that we converted to decimal from binary on the last screen. So in this case, what we do is notice that I broke up this byte into what's called nibbles. A nibble is 4 bits long, not 8 bits long like a byte. So we'll take a byte and break it up into 2 nibbles. And that value is easier to calculate because you never get above 15. It goes 1248, 1248. That's a full byte there. Let's take a look. In this first example, we have no bits on here and no bits on here. So our hex value is actually 00, isn't it? This is my decimal values here. So my hex values are 00. In this one, I have 0 in the first nibble, but I have all my bits on in the second byte. So that makes 8 and 4 plus 2 plus 1 is 15. So we actually have 015 as our hexadecimal number. But hold on, we cannot use that as a number because it would be 015. It has to only be 2 hex characters. Hexadecimal number systems use 0 through 9 and A through F. 10 equals A, 11 equals B, 12 equals C, 13 equals D, 14 equals E, and 15 equals F. So in our last example, our number was 015 or 015, so our hexadecimal equivalent to that would be 0F, wouldn't it? Now you might see it also preceded by 0x, which means the next characters are in hexadecimal. Because if your actual answer was 66, you wouldn't know if that was decimal or hexadecimal. So if I said 0x66, then you would say, okay, that's hexadecimal. Let's take a look at the next example. On our third example here, we break this up into nibbles. We have the 1 and 4 bit on, that's 5. And here we have the 1 and 4 bit on, that's 5, 5. So the answer would actually be 0x55. The next example, we have the 8 bit on, and here we have the 2 and the 1, so the answer would be what? 8 and 3, or 0x83. The fifth example, the answer would be 1 and 6, 0x16. In our last example, what would that be? 0x, everything's on, so it would be what? FF, or 15 and 15. So we can see our decimal and hexadecimal equivalents. Let's take a look at another screen and do a little more practice on 3 more examples. What is the decimal and hexadecimal equivalent of the following binary numbers? So we have to add these up. Let's first do decimal, and then we'll do hexadecimal. On this top one here, again, I like to start at my largest number. 128 and 32 is 160, plus 16 is 176, plus 8 is 184, plus 2 is 186, plus 1 is 187. So my decimal is 187. Now I need to break this down the middle into nibbles. So I have 1011 space 1011. This is 8 and 2 is 10 and 1 is 11 and 11. So what is 11? Baker, Baker, or 0xBB, isn't it? So this one was 187BB, 0xBB. The next one is 128. I said 3 example, and there's 4 here, isn't there? Anyways, the next one is 128 plus 16 is 144, plus 8 is 152, plus 4 is 156, plus 1 is 157. So you can see this takes some thought to add these all up. But let's break these up now into nibbles. So this is 1001 space 1101. So what is this one? 8 plus 1, this is 9. And 8 and 4 is 12, plus 1 is 13. So 0x9D. The third example here. I have the 64 and 32 bit on, that's 96. Plus 4, it's 102. So the decimal equivalent answer is 102. Let's take a look at our hexadecimal answer. This looks like 1248, and again 1248 if we break this down the middle. The answer to this is actually 0x66. That was the example I gave earlier, and the reason we use 0x in front is so we know it's hexadecimal characters. Let's take a look at our fourth and final example. We have the 128 and 32, that makes 192, plus 8, that's 204, so we have 204 as my decimal answer. And we break this right down the middle, and these actually are the same, aren't they? 1100, 1100. That's 8 and 4s, 12 and 12. That is 0x, Charlie, Charlie. So if you need any more practice, just write out some binary numbers, just randomly make them up, and add them up decimal and add them up in hexadecimal. Now let's talk about the physical layer. The physical layer takes bytes from the data link layer and sends them on into bits. So remember, we have bytes, or we're going to call frames. We take the bytes from the frames and turn them into bits at the physical layer. Then we send them out one bit at a time in a digital signal on the network medium using a clocking and timing method. And lastly, let's talk about data encapsulation one more time. Let's take a look at this. I've mentioned this before in this section. In this part, we've talked about the data encapsulation method, how data is encapsulated from the application layer all the way down through the physical layer. The upper layers have a data or data stream that is handed down to the transport layer. The transport layer will put a TCP or UDP header on it depending on the type of data it's going to be. At this point, once the header is put on it, it is called a segment. This segment of data is then handed down to the network layer to be routed through an internetwork. Once an IP header is put in front of this segment, it is now called a packet. This packet is then handed down to the data link layer to be put onto the local network. The data link layer then takes a frame and puts it into bits and sends it down one at a time to be put onto the network medium. So again, our data encapsulation method is data, segments, packets, frames, bits. Let's say that again. Data, segments, packets, frames, bits. You must remember your encapsulation method.